let's start with this short introduction. And let's see, for instance, what are the units of information in quantum computing, as we are expected to give some highlights on quantum computing. Let's start from what we already know. A classical bit is binary. It can take one of two states. It can either be state 0, let's say a coin side like head, or it can be state 1. For the same coin, it's the other side, tail. The quantum computer is built from logical elements called qubits, which is the short for quantum bits. A qubit is binary in the sense that it's realized using a quantum coherent two-state system. And it can be set in state 0 or in state 1 that corresponds to the call of the Bloch sphere we can see in this nice picture. A qubit can also be a quantum superposition state, that is a single state, but it carries aspects of both state 0 and state 1 simultaneously. All points in the surface of this Bloch sphere represent a superposition state. Superposition state results in probabilistic measurements, meaning that if we have, say, an equal superposition of 0 and 1, and we measure the qubit, we have a 50-50 chance of measuring state 0 and then 50-50 chance of getting state 1, like a toss of a fair coin. When we measure the qubit, we destroy the superposition state. We have another special feature of the quantum world that is called entanglement. We can create a strong correlation between a pair or a group of qubits in such a way that the quantum state of each particle cannot be described independently of the quantum state of the other particles. The pair behaves like a pair of linked coins that drop on the same side simultaneously. When we measure both members, we find that the results always agree. And we can get the results even if great distances separate the two systems, and the measurements are performed nearly simultaneously. So how many states can we represent with n qubits? A classical computer can represent only one of these n-bit states at a time. Processing multiple n-bit states can either be performed sequentially in time or in parallel using additional copies of the hardware. This is classical parallelism. In contrast, the qubits in a quantum computer can be set into a single superposition state that may simultaneously carry aspects of 2 to the power of n components. This enables two uniquely quantum mechanical effects: quantum parallelism and quantum interference. And this is the road. How do we represent the logic structures in QC? Classical computers perform arbitrary Boolean logic with a small set of single bit and 2-bit logic gates. As far as universal quantum computation is concerned, it can be built from a small subset of these types of single or 2-qubit gates. A universal state gate set enables us to perform any type of algorithm, quantum or classical, on a gate model quantum computer. Single qubit gates are unitary quantum operation on single qubits that can be represented as rotation in the Bloch sphere we saw before. 2-qubit gates are unitary quantum operation on 2 qubits. When this gate cannot be written as a product of 2 single qubit gates, they are called entangling gates, and they exploit entanglement to create strong correlation between qubit states. In quantum information theory, a quantum circuit is a model for quantum computations, similar to classical circuits, in which a computation is a sequence of quantum gates, measurements, initialization of qubits to known values, and possibly other actions. What are the current limitations of QC? Currently, we are in the noisy intermediate scale quantum era, and quantum computers are affected by noise, by errors. They are not fault tolerant. Over time, the qubit begins to interact with its environment. And as the time goes on and the qubit is subject to more of this environmental noise, eventually we cannot longer recognize its state. And the quantum information is fully lost. This behavior will be visible as error when you do calculation. Here we see in the image that there are two processes by which a qubit loses in quantum information. The first is called energy relaxation. That is a qubit in its excited state tends to relax back to its ground state 0 by emitting energy to the environment. And on the Bloch sphere, you see that the qubit spans from South Pole to the North Pole. For this energy loss. Another way a qubit loses information is through the coherence. A qubit starting on the equation of the Bloch sphere might move along the equator away from its original position. This is called dephasing. And when it does so, the qubit experiences noise that alters the qubit state in a way that we didn't anticipate. And to prevent this behavior, there are techniques such as error mitigation that reduces error that occur during computing, and error correction that restores the computation after an error occurred. They are among the most active area of research at the current day. What problems can be solved in QC, in quantum computers? Quantum computers are ideally suited to solving complex problems, which are hard for classical computers. If we have to measure how efficiently a computer can solve a given problem, this efficiency is determined based on how the computational resources grow when they are needed to solve this problem. And one of the main reasons of the current interest in quantum computers is that certain problems can be solved in polynomial time on a quantum computer, even though the best known classical algorithm for the same problem requires exponential or sub-exponential time. So a quantum computer is an accelerator for only some types of problem, not a general purpose computer. The challenge now is working out what quantum computers can be best used for. As with any new tech, there is no easy answer. Anyway, quantum computers will be particularly good at tackling certain problems that are difficult or even impossible for classical computers to solve, like quantum chemistry. And powerful, cost-effective quantum computers will be also great at solving special algorithms, at using special algorithms to solve complex optimization problems, such as scheduling, routing, and logistics. And these algorithms involve seeking the optimal solution from lots of possibilities. And even AI will be sped up by quantum computing, as there are new formal proofs that training in a quantum neural network requires only a small amount of data, in contrast with classical computing, huge appetite for data and machine learning. Quantum computers can be applied to many types of simulation problems. The challenge is that many of these problems require a large number of resilient qubits, and such a large-scale quantum computers are still likely some years away. Before we get to the point that we can simulate systems entirely on quantum computer, there are room for hybrid classical quantum systems to hold a quantum advantage over purely classical algorithms. One example of that is called a parational quantum eigensolver. Classical quantum computers are passing information back and forth through the simulation like a Pong match. Therefore, the quantum computer is acting as a coprocessor. it need not to be coherent over the entire duration of the simulation, but only over the period of time it takes to produce a single trial state, obtain the necessary observables to calculate its energy. And this approach allows useful computation to be done in the nearer term using less reliable noisy qubits. What types of quantum computing can we use by now? So if we restrict ourselves to universal quantum computer, there are a variety of physical systems that have been proposed as qubits for quantum computer. There are many ways of building a quantum coherent two-state system. In spin qubits and in these centers, we are exploiting electrons and nuclear spins. For ion traps and neutral atoms, we are utilizing atomic states. Superconducting qubits are based on electrical circuits, such as nonlinear oscillators that behave like atoms. There are other qubit modalities, such as topological qubits that are currently under study. But we cannot see any accessible hardware to test them. And there are, aside from universal quantum computing, we still have other possibilities to explore. Analog simulators are quantum computers that can simulate a quantum system using both digital gates and analog evolution. Alternatively, the qubits themselves and the way they connect to one another and the strength of those connections can be designed to emulate a system behavior. So we can model an Hamiltonian on an analog QC, tuning all these parameters and find a ground state. Quantum annealer, also known as a adiabatic quantum computer, is a different type of computer that addresses classical optimization problems by mapping them onto a set of interconnected qubits. And then they search for a solution that minimizes the total energy. And the idea behind quantum annealers is that we have a quantum system that is governed by one Hamiltonian, and we can transfer the system to another Hamiltonian by changing the system parameters. And if the transition is done slowly enough and the system has no noise, the computer will remain in its ground state throughout the evolution. And we have also photonic quantum computing with linear optics that use photons as qubits. Photons have the advantage of minimal decoherence. However, they don't naturally interact with one another. So in order to make two qubit gates, an effective interaction need to be induced. Photonic processors use Q modes, which are a different way of carrying and manipulating quantum information that qubits. A Q mode is a quantum mechanical harmonic oscillator represented by a light beam. Encoding qubits in Q modes is not unique. There are many ways of doing that. And the way in which Q modes have their state space structure is completely different from qubits. That's why this realization is still considered a chapter apart. So consider all this realization. There are many parameters to take into account if we have in mind to address a specific hard-to-solve real-world problem with quantum computing, and in general, hybrid computation. As the hardware landscape is really heterogeneous, and the number of qubits in characterization is low, we need to look for the best fit of the algorithm we are developing versus the target quantum computing realization.